All right, let's get started. So this is chapter 6, and we talk about AC signal. AC signal. So in digital, we are happy with DC and DC voltage and current. DC voltage and current. Okay, in digital. Now we're moving to the analog. So analog part. So we need to talk about AC signal there. Okay, alternating. So it goes continuously like this, and this kind of signal, AC signal. In digital, we used to have this, right? 0, 1, 0, 1. Okay. Okay, this is digital world. This is analog now. Simplest wave is sinusoidal, right? We call it sinusoidal. Okay. Yeah, so analog is the heart of the digital electronics, okay? Because even nature is analog, okay? Nature is analog, not digital. Okay, and we have seen lots of devices that are directly driven by AC signal, right? So lots of devices that are driven by AC signals. So the simplest is sinusoidal. So which is of the form of this: voltage Vt equals V0 cosine omega t plus phi. So we call it sinusoidal because even though we have cosine here, right? Instead of saying cosinusoidal, instead of calling cosinusoidal, we call sinusoidal because cosine and sine function, they differ by just phase, right? They're exactly same. So this is sine function, and cosine starts at 1, right? That's the only difference, but everything else is same. So at t equals 0, cosine is 1. At t equals 0, sine is 0. That's the only difference, but the appearance is the same. So instead of calling cosinusoidal, we call it sinusoidal. Okay. Here B0 is the peak voltage. This is the peak voltage. This is B0 is this guy here. This is B0, the peak. Okay. So the voltage varies from 0 to V0. Okay. And the omega, this omega here is 2 pi f. Omega equals 2 pi f. Okay. This is called angular frequency. Angular frequency. And this guy, this f only, okay, this guy only is simply called frequency. Okay, and this this is called this phi, right? This is phi. This is called phase. Okay. So, and if you multiply this guy by 2, right? Let's say V0, right? Then if you also add V0, not the sign, but the magnitude only, this is V0 also, negative V0, right? So what is the total length here? V0 plus V0, right? Which is 2 V0. This is called peak to peak voltage, okay? Peak to peak voltage. All right. All right, this is the thing we talked about now. In this case, what is the phase offset? Let's see, this is the same thing I talked before. This is nicer form. So it doesn't start at 0, right? See this wave, it starts at somewhere here. Okay. If you consider from here to here, here to here is one cycle, or here to here is one cycle rather, right? It's the same thing. You know, find the identical points. Peak and peak, they are identical. And this guy and this guy are also identical, right? Okay. So that's what I'm trying to say. So from here to here is 360. Okay. From here to here is 360. Let me do peak to peak. That will be easier. Okay. So from here to here is 360. If this is 360, this halfway through is 180. Okay, halfway through is 180, right? This is 180. This is 180. This is 180 makes 360. And how about this guy? This guy is 90. Okay. And the half, what is half of this guy here? That is 45, right? This is 45, right? So this is exactly 45, okay? So they are exactly the same, right? See that? So this offset, phase offset is 45, pi over 4 in radian. Lucas, did you say something?
I did not.
Okay. All right, guys. So any questions so far? Yeah, so this is the animation that how the sinusoidal work. So if you just look at this guy here, this guy, what is this guy? Very hard to catch. This yellow thing, right? Just take a look at this just yellow thing. So what is the motion of the yellow thing? Don't look at anywhere. If you look at the yellow thing, okay, this yellow thing is doing up and down. Okay, but at the same time, this is going across this yellow thing. I couldn't catch it, sorry. So this is the yellow thing. It is doing up and down, right? Okay, but the thing is, at the same time, it looks like it's traveling in this wave, right? See, this yellow thing is traveling. This is the nature of sinusoidal wave. Okay. All right, so we'll define some terminologies here. Okay, so first of all, we talk about root mean square value of the time varying voltage, because we know that for voltage varies, right? Okay, like that. Meaning, so the voltage varies, you know, 0 to maximum. Okay, in the case of this is one of the examples of our like AC signal, right? The bulb, light bulb. Okay, light bulb. So the voltage varies 0 to maximum. So when the voltage is 0, okay, what must have happened is what should have happened is the light bulb should turn off, right? So why doesn't that happen? Any question? Any answer to it? I said alternating current voltage varies from 0 to maximum, right? When the voltage is 0, why don't you see your light bulb turning off?
Because the voltage doesn't stop there? Like it's continuing past that?
No, but so you should be able to see the light, like turn off the bulb, right? It's the switch off, right? Switch off is no light, no current, no voltage, means this should completely off. So at some point, you should be able to see this off, right? But we don't see it. Our light bulb glows all the time. Why is that? Because this happens so fast. Okay? Because this happens so fast. What is the frequency of the AC? You know, it's 50, depending on which country you are in, 50, 60 hertz, right? 50 or 60 hertz. Meaning in 1 second, right? In 1 second. So you'll see 50 of them. In 1 second, you will see up and down 50 times. That's too much fast, right? So this happens 50 times. One cycle, you see, it's 1 cycle. You should see 50 of them or 60 of them in 1 second. That's too fast that you don't even notice this 0. Okay, all right. So now the voltage varies from 0 to maximum, but when you measure the AC voltage, your multimeter does not give you fluctuating voltage, right? Okay, when you measure the AC voltage using multimeter, right? Using multimeter, do you see fluctuating voltage like this? No, you don't see that. What happens is that multimeter, it measures the RMS value. It measures the RMS value of the AC voltage. What is RMS? RMS is calculated like this. So where BT is this guy, this is BT. See, it varies with time. This is your BT. That's what BT is here. BT squared, take the, what should I say here? Take the integration, right? Antiderivative of V squared and divide by T and take the square root. Okay, it's kind of average, right? 1/2. If you have this, suppose you don't have this, right? You don't have this 2 and 1/2. Okay, ignore these two things, these two numbers, 1/2 and 1/2 and 2. If you ignore these two, then what are you left with? You are left with 1/T 0 to T BT dt. So this is just called average, right? Calculus 1, right? Okay, this is how you define your average in calculus 1 or calculus 2, maybe calculus 2. Okay, but you have squared, then take the, after you take the derivative, sorry, not the derivative, the integration, after that you take the square root. Okay, so this is the definition of RMS. Okay, so this RMS is measured by the multimeter here. Multimeter measures this RMS value. Okay, so if you plug in this BT here, BT equals, what is the sinusoidal? So in the case of sinusoidal, what is your BT? BT is, help me here, V0 cosine omega t plus phi, right? If you plug this in here, and do the integration, then this happens to be equal to this guy here. Okay, you can do this integration at home, okay, if you want. So if you do that, I'm not going to do this because, you know, this is not calculus class. Okay, so remember we say our voltage voltage is how much? If you have standard wall outlet, right, in our house, then what is the voltage there? We say 110 voltage, right? 110 volt, right? What is that 110? That 110 is the RMS. Okay, RMS value. This is how you calculate the RMS value. Then similarly, what is the RMS power? So what is the power? How do you define the power? Power equals V square over R, right? So that's why power average or RMS power is, or RMS, you can say RMS or average, is equal to RMS over R, where L refers to load resistor. Okay, we'll talk about loading in the next chapter. Okay, so for now, just consider this is load. Okay, this is load resistor. So we talked about two things here. We talked about voltage. We talked about power. Okay, power and voltage. So sometimes, you know, the power is watt, right? Power is watt, and voltage is so voltage is volt, right? Sometimes we express them in terms of different unit, okay, which is decibel. So if you want to compare two signals that vary by order of magnitude, let's say, you know, let's say the one voltage is 1 volt, the next voltage is, you know, 100 volt. So what is the difference here? The difference is 2 order of magnitude, meaning 2 to 10 to the 2, right? See the difference? So this is called 2 order of magnitude. So if you have such kind of voltages, then to compare those voltages, instead of using volt, we use decibel, okay? Which is defined as this. Decibel in terms of voltage is defined like this. Similarly, you can also define the decibel for the power, okay? And that will give you this one. This is the decibel in terms of power, and this is the decibel in terms of voltage. But they are exactly the same thing. Okay, you can do the calculation because power is what? Okay, let's begin with this one. So you have dB equals 10 log P1 over P2, right? So what is your P? P is B square over R, right? P is B square over R, see here. So then 10 log P1 is B1 square over R, P2 is B2 square over R, then R and R cancel out, then what are left with here? You're left with 10 log B1 over B2 square, right? Use the log property, then this 2 comes in the front, right? Multiply with 10, 20 log B1 by B1 over B2. So you get this one here, okay? This is equal to that. This is how you can prove it. Question here, right, so far? Okay, now here we're talking about rectangular AC signal. Okay, not the sinusoidal, right? But the rectangular. So this kind of, okay, this is a rectangular AC. So if you have rectangular, then so this is rectangle, not a square, right? Not a square. So meaning this not equal to that. Okay, so this is THI. For the time equals THI, the signal remains high. For the time equals T low, the signal remains low. So they are not equal. That's why this is rectangular. Okay. So again, the voltage varies from 0 to V0. This is V0. This is 0. This is V0. Now in this case, we can define the duty cycle. The so-called duty cycle. Duty cycle is defined as T high over T. What is the total time here? Total time is, this is T, right? T equals T high plus T low. Okay, and this divided by this T. Okay, T high divided by total time. T high divided by total time, where total time is this guy here again, right? That quantity is called duty cycle, and we represent that by D. Okay, so the average voltage in the case of rectangular, how do you define the average voltage in the case of rectangular? Is V0D. Okay, how do you do that? Because average, how do you define average? 1 over T V Vt dt, right? This is how you define average. Calculus 2, calc 2, right? This is how you define average. Now in this case, what is your, you can write this guy as 0 to T high plus T high to T low, dt. Okay, what is this guy? From 0 to T high, what is the voltage here? From during this time, you use your voltage. What is your voltage? V0, right? V0. During this voltage, meaning T high to T low, what is your voltage?
0.
That's why this guy is 0. So you are just left with this guy, the first one. 1 over T. What is this guy? V0, T high, or V0, T high over T. What is this guy? Duty cycle, V0D. Okay, that's how you get the average voltage. Okay. Similarly, you can find the RMS value. So how do you define the RMS again? Define similar to average, but you have to square the V square and take the square root, right? So you have to square, then take the square root. See? So you have to take the square and square root. That's how you define the RMS. So 1 over T, 0 to T integration, okay, square dt. Then again, same way. So again, this Vt is V0 during T high. After that, you don't have to integrate, it will be 0. That's why you get this one here. Okay, so your T, this is T high, because during the T low time is already gone, right? So that's why you get 1 over T V0 square T high here. So what is this guy? 1 over T V0 square T high. This guy is T high over T is D. So V0. So this happens like this. V0 is square is here. Then T high over T square root. So this is V0. And this is what? Square root of D. That's what we have here, VRMS. Similarly, what is the power? Power is simply V square over R, right? We know the formula. Okay. So power equals V square over R. So in this case, V is this is square. which is B squared D, right? That's on the top. Then R is RL. We call it, load resistance. We talk about the loading in the next chapter. Next chapter or this chapter, I don't know, but we'll talk somewhere, okay? All right, so guys, question, I have been talking.
I have a quick question.
Please.
When doing those calculations here, like finding the average voltage, can you do those calculations in decibels?
Calculations in decibel. Yes, you can. The thing is, we use decibel if we are comparing. Okay, most of the time. So you don't have any comparing. So we're just talking about only one signal here, right? One signal.
Right.
So if you talk about two signals, let's say two signals, you are comparing two signals, and those two signals have, let's say, one signal is, let's say, the peak voltage for the one signal is, let's say, 10, right? For the other signal, the peak voltage is, let's say, 100. Okay, they are of the order of, they differ by one order of magnitude, right? Because this is 10 to the 1, this is 10 to the 2. So they differ by 1. Okay, in this case, you normally use decibel. But
Oh, okay, I see.
get that?
Yeah, thank you.
All right, you're welcome. Okay, now let's talk about capacitor in the AC circuit. So far we have been talking about capacitor in the DC circuit, right? We never talked about a capacitor in the AC circuit. So let's say we know, let's say your B, let me start with my B, T is V0 sine omega T, okay? I consider the phase is equal to 0. V0 sine omega T. What did I miss? I missed phi term, right? Did you see that? I missed phi. Okay. So yeah, this is my, last time I considered V0, Vt equals V0 cosine omega T plus phi, right? But I can consider, anything. You can consider cosine, you can consider sine interchangeably, because they're just the same thing, right? You can use cosine and sine interchangeably, because when you say cosine, this is what it is. Okay, when you say sine, then you have this slide. That's it. That's the only difference. But they look exactly the same. The sine starts at 0, cosine starts at 1. That's the only difference, right? But they are exactly similar. That's why you can use this form or this form interchangeably, okay? It doesn't matter, whichever you use. So in this case now, I started with sine now, okay? So, but the thing is, I consider my phi equals 0. This phi, remember I used to have phi? This phi equals 0. What does that mean? Phi equals 0 meaning at time t equals 0, the voltage is 0. At time t equals 0, V is 0. That's the meaning of phi equals 0. Really? Let's check. This is my sine function, right? See, at t equals 0, my V is 0. Yes, that's correct, okay? That's why I don't have to write phi there. So even though I write phi there, my phi is 0. Okay? You can simply write 0 if you want. Now, so the thing is, now I'm trying to relate current and voltage, right? I'm trying to relate current and voltage. So this is my voltage. This is my voltage. So what is the current in the capacitor? This is the capacitor. What is the current through the capacitor? What is the definition? I know current is I, right? I equals dq over dt. That's the definition of current. Now, what is your Q here? What is the capacitance defined? How do you define the capacitance? Q over V, right? Then from here, what is your Q? Q equals CV. Okay. So we have dq over dt. Then d over dt, derivative of Q is CV. Then your C is constant. You can take it out. Then you have dV over dt. That's your I. Okay, that's your I. Current, right? So can I use this formula? Can I use this formula here? Because I know this is my voltage, right? This is my voltage. What is the derivative of this guy? Help me here. So C, what is the derivative of V here? Your V is this. Your V is this guy here, right? This is your V. What is the derivative? V0. Then what is the derivative of sine? Cosine omega t. Then you have to use the chain rule. What is the derivative of that guy? Omega, right? So let's put the omega right here. So C omega V0 cosine omega t. Okay. Now I want to change it to sine. You know why? Because I started with sine here, right? That's why I want to convert this cosine to sine. Because I want to compare. Okay. I can compare just banana with banana. I cannot compare banana and pear. Okay. So that's why I want to change this to change this guy to sine function. So how do I do that? How do you change your sine to cosine? This way. Okay. So what is sine 90 plus theta? Remember trig cosine theta, right? That's what I did here. Sine pi over 2 plus omega t theta, which is cosine t. Now I change it to sine. Okay. So this is sine, this is sine. But the argument here is omega t. Argument here is omega t plus pi over 2. Okay. Now I'm going to tell you, I'm going to discuss here. So if the voltage is sinusoidal, the current is also sinusoidal. I can rewrite this guy as this. This guy can be written as this. I0 sine omega t plus pi over 2. What is my I0? I0 is this guy here. V0 omega c. That's your I0. Okay. Now they are similar. These guys are similar. These two guys are similar. This guy and this guy. So V0 is I0 and sine argument is omega t here. Argument is omega t plus pi over 2. Now I'll ask the question here. A time equals t, a time t rather. Okay, this phase of I is, what is the phase of I? Omega t plus pi over 2. At the same time, what is the phase of V? Omega t. Which is bigger?
Omega t plus pi over 2.
So meaning, so I is bigger. Meaning I leads. I leads V. Let me write this down. I leads V. Or I can write this guy as V lags I. It's the same thing. You can say I leads V or V lags I. It's the same thing. Okay. So this is how you figure out leading and lagging. So this is the conclusion. If V is sinusoidal, then current is also sinusoidal. But what is the difference? One difference is amplitude. Amplitude of I is this, amplitude of V is this. Okay, V means this is the amplitude. This is the amplitude for the V, which is V0. What is the amplitude for I? For the I, amplitude is V0 omega C. That's the amplitude of I. That's the one difference. The other difference is phase. The phase of V is omega t. The phase of I is omega t plus pi over 2. Meaning I leads V or V lags I. It's the same thing. So what does that mean actually? So what does that mean physically, right? Let's say it. So let's see. So you have to compare these two guys, right? You are comparing these two guys. So this guy is this guy is this guy here, which is this, right? Okay. And this guy is exactly this guy. Now we are comparing these two. So here, find the identical point in these two. Identical point. So you are staying here, right? You are staying here. You are standing here. Okay, you are standing at the origin. And find the identical point. So I think it will be easy if you find the point on the x-axis, right? Okay. So which point is identical? Find the first identical point on the x-axis. This one, see, is going down and touches x-axis. And this also goes down and touches x-axis. These two points are identical. Remember, I want to warn you guys, these guys are not identical. These guys are not identical. No, these guys are not identical. Because why? Because this point also on the x-axis, this also on the x-axis, right? They are not identical. Why? Because this point we get after, see, this guy goes up and get to that point, right? See? Going up, get to that point. And this point going down and it touches the x-axis. Even though they have same x equals 0 or t equals 0 in this case, they are not identical. Okay, you have to find exactly identical point. Okay, going down, you see this guy, the wave is going downward, touches the x-axis. The wave is going downward and touches the x-axis. There, these 2 points are identical. So what I'm trying to say here is, okay, let me summarize. So you are standing here, find the first identical point on the x-axis. Why did I choose x-axis? Because it's easier. Okay, then you are standing here and find the first identical point on the x-axis. Okay, now from here to here, what is the distance? AB. From here to here, what is the distance? CD. Which one is bigger? CD is bigger or longer, or AB is longer? Which is short time, right? The CD is, this is time axis. CD is short time. Shorter time rather, right? Shorter. AB is longer time. So what does this mean? Voltage takes longer time to cross the x-axis than the current. Which one is slow? Voltage is slow or current is slow? See, voltage takes longer time to cross the x-axis than the current. This means voltage lags, right? That means voltage lags the current. That's the meaning. Question here, please.
Is there ever a time where the voltage doesn't lag?
Yes. Yep.
Cool.
So that's a very good question. Remember, we're talking about capacitor, right?
Mhm.
So we have a capacitor in the circuit. Now we'll go to the next thing will be, what are the three basic components in the circuit? We have capacitor, we have inductor, we have resistor, right?
Mhm.
So we'll talk about all of this one by one. So when you talk about them, the rest of them, then you'll see that. Okay, for the capacitor, voltage always lags current, period. That's the thing, that's the conclusion.
Gotcha. Thank you.
All right, so then what is your I0? I0 is this guy, right? As I said earlier, this is I0. I0 is this. Then let's define, let's use the Ohm's law here. What is Ohm's law? Help me here, I need help. I equals V over R, right? Did I write, is it correct or is not? I think this is Ohm's law, right?
Yeah.
Yeah, so here, what is your, okay. So now how I want to write this guy in terms of this guy. Can I write this guy as this? B0 over 1 over omega C. So that I get this. In this case, my R is 1 over omega C. Do you see that? That's called RC. That RC is called capacitive reactance. We don't call it resistance anymore. This guy is resistance, right? So, but in the case of capacitor, we call capacitive reactance. Capacitive reactance is given by 1 over omega C. Question here? Now let's talk about the inductor in AC circuit now. So we have the inductor here. So this is the inductor, right? This is the inductor. We have AC signal here. We have the inductor connected in the circuit. Now, let me begin with I equals this. I have a reason to select this. This is sinusoidal, right? So I consider I equals I0 sine omega t plus phi. Okay? Instead of this pi is negative in this case. Phi is negative pi over 2. That's why you get minus here. So I started with I. Why? Because in the case of inductor, we have the B given by this. This is your B. The voltage across the inductor is given by L times di over dt. See that? L times di over dt. We have to find the derivative of I. That's why I need I here. Okay, I chose this I like this. Why did I choose this minus pi over t? It will be clear in a second. Okay. In the previous case, remember in the case of capacitor, I simply chose voltage like this. Now I have chosen the current instead with the argument this. Okay, because I have to take the derivative of current. In the previous one, I had to take the derivative of voltage. That's why I chose this one. In this case, I have to take the derivative of current. That's why I chose this one. Okay. Now, when you take the derivative of this guy, what do you get? Help me here. So what is the derivative of this guy? Di. So what is your B then? B equals L is L, right? L is L. What is di over dt? I0. What is the derivative of this guy? Help me here. Cosine omega t minus pi over 2. Then the chain rule, right? Do the omega here. So you have omega somewhere here. Sandwich this guy here. So you have this guy here. L omega I0. Okay. L omega I0 cosine omega t minus pi over 2. That's what it is. Now again, I have to change it back to sine, right? Because I want to compare. That's why I want to change this back to sine again. So when I change it to sine, what do you get? Cosine theta minus 90 can be written as cosine 90 minus theta, right? Why? Because cosine theta minus 90 equals cosine minus 90 minus theta, and which is cosine 90 minus theta. Remember? So cosine minus theta equals cosine theta. If you remember this, then you can do this, right? Then using that, I can send this guy back to sine form, which is this. Okay. Now you understand why did I choose this pi over t, minus pi over t, because I get omega t now. Remember? Exactly the same thing I chose here first. See? Sine omega t. Exactly I got sine omega t here. Okay, now I want to compare these guys. So which one lacks now? At time t, okay, I is what? What is I? I is omega t minus pi over 2. At the same time t, what is your v? Omega t, which is bigger? V is bigger or omega, this guy is bigger?
V.
So that's why B leads I here. B leads I, or I lacks V. So that's what it is. So voltage leads the current. Okay, in the case of inductor, voltage and current, they are both sinusoidal. That's the one proof, right? That's what we showed. If the current I is sine, then voltage is also in the sine form. But this is V0, by the way. This is V0. V0 equals I0 omega L. So remember, V0 equals IR, V0 equals IR, right? V equals IR, right? So you have this guy is R then. So this is I, this is R. So what is this guy called? RL equals omega L. That is called inductive reactance. Okay. Similarly, lagging and leading behavior can also be seen from this diagram. Suppose you are here. So you look at this guy again, right? The first downgoing point. From here, what is the first downward going point? That means the x-axis. This is the point. Then from here, what is the first downward going wave? This is not downward, this is upward, this is upward, this is upward, then downward. This is the first one. Okay, first downward going wave. So if you look at those two, then this guy is AB, this guy is, let's say, CD. So current takes longer. Current takes longer to reach the x-axis. That's why current lags or voltage leads. Guys, question so far? So far, so good.
Yep.
Okay, now let's talk about complex number. Why do we need to talk about complex number? That complex number makes the calculation less complex. Complex numbers make the calculation less complex. That's the good news. Even though we call it complex number, so those complex number, so you know complex number, right? Have you guys done complex number anywhere?
Yeah.
So A plus IB, right? That's the complex number.
Yep.
So you have your regular number is like 2, 3. It's not like that, right? You have to add, let's say you can make complex number by using these two numbers. So 2 plus I3 or 3 plus I4, like that, right? So that kind of thing, complex number, because it is little complex than our normal number. That's why we call them complex number. But these complex numbers are meant to simplify our calculation a lot. So you will see that in a moment. Okay. Now let's talk about the complex number. Let's briefly talk about complex number. So complex number can we represent? This is a complex number, right? I said this is complex number. Complex number can be represented in the xy plane. So x is real part and y is the imaginary part. So in this case, 1, 2, 3, and 1, 2, 3, 1, 2, 3, 4. So this point is represented like this. So you have 3 here, 1, 2, 3 here, 1, 2, 3, 4. So this guy is 3, 4. Okay, that's how you represent the complex number, like this here. So this x p is 3, 4. Let me erase this. This is okay. So x is, this is called x. X is if the length from here to here is a, right? Length is a. If this is 3 and 4, what is the length? Use the Pythagorean theorem. This will be 5, right? 3 square plus 4 square equals 9 plus 16. Then you have to the square root, right? Then this is 25, which is 5. So that's what it is. So this is 5. Then our a is 5 in this case. So a equals 5. P is 3, 4. Now this is x. This x is 3, right? So 3 equals a sine phi. So in this case, a is 5, right? Okay. So what is the value of phi? Can you find your phi? If this is 3, this is 5. Okay, so we'll wait a little bit. So let me do that. Sorry, did I make mistake? I made. This is cosine, right? This is cosine, this is sine. So this is cosine and this guy is, this is sine, okay? A sine phi. So to find phi, what do you do is, you have x equals a sine, a cosine phi, y equals a sine phi. So what happens if we divide y by x? If you divide y by x, what do you get? Okay. So you have 10 phi, right? 10 phi equals a sine phi over a cosine phi, which equal to y by x. Okay. You don't, if you want to find the phi, you simply do 10 phi equals y over x. So in this case, 10 phi equals, what is y? Help me. 4 over 3. So what is your phi then? Inverse tangent 4 over 3. So which you get 53.13 if you do that. Right there, what is I? How do you define your I? I is square root of -1, right? That's your I. Question here. No, so far so good. So this guy can be written as a cosine phi plus I sine phi. So this guy can be written as a e to the I phi. I called, so this formula, remember this formula? So let me conclude here. This is awesome. Cos phi plus I sine phi can be written as e to the I phi. This formula is called Euler's formula. E-U-L-E-R-S, Euler's formula. The scientist, mathematician, he found this formula. This is your Euler formula. Whenever you see cosine phi plus I sine phi, you can simply write this guy in terms of this. I'm very happy. I'm very excited. Why I'm excited? There is a reason behind it. So if you want to find the derivative of this guy, what do? Find the derivative of dy by d phi. What do you get? You don't have to find the derivative of cosine and sine. You have to just find the derivative of e to the I phi. Boom. Do the integration. Again, you get the same. What is the derivative of e to the x? Derivative of e to the x is x. E to the x. What is the integration of? What is the integration of e to the x? Again, same thing. See that? That's why I'm so excited now. Because instead of doing this kind of integration, cosine and sine, right? You just do the integration, get the same thing again. Do the derivative and get the same thing again. How cool is that? Okay. So that's why what we do here is we use a Euler formula again and again. So I love Euler formula because I don't have to do derivative and integration. That's to give me same thing again and again. Instead of talking sine and cosine, remember we talked about sine and cosine here. Look at that. We talk about sine and cosine. Okay. Look, instead of talking sine and cosine, we just talk about E now. Because it's very easy to deal with. But the thing is, you might ask me a question. Okay, if this is the case, let me go here. Let me start with this one. If this is the case, okay, if we say this is as this, right? Okay, I'm excited now. I'm rewriting this guy as this, e to the I omega, right? I omega t. Right? The thing is, they are not same because I omega t is what? E to the I omega t is cosine omega t plus I sine omega t. How come e to the I omega t is equal to sine omega t then? Because I just need sine omega t, right? How come you can use this guy? How about this, right? How about this I? You might ask me a question, right? I'll be happy to answer that question if you ask that. My answer would be, so I do the calculation, all the crazy calculation, and finally I'll get something like this. I don't know, cosine omega. And this is just an example, okay? This is a real life example. Let's say, I don't know, omega t plus 2, I sine omega t. I don't know. I came up. I had to do something, right? Some calculation. Then finally my answer is this. Then what is your answer then? Your answer would be because remember I started with sine omega t, which is what? Imaginary part of this guy. I started with sine omega t, which is imaginary part of this guy. That's why when you reach the answer, you take the imaginary part only. There. Your answer would be 2 sine omega t. Boom. You just ignore this. Because you started with the imaginary, you ended up with the imaginary. Boom, that's the answer. See, this I equal to I omega t is so it acts as it's a tool. It's awesome tool, so that you can handle nasty problems. I love it. Guys, so far so good. Any question?
So then for on the slide you were just on, it would be for when it's cosine, it would be just one more back, it was omega t, right? It would just be e to the omega t.
E to the omega t.
For current.
Or here, you said here.
Yeah.
Okay. This.
Or it would be that whole thing, omega t plus pi over 2.
Yeah. So you have to take the argument. Okay. So if
Okay.
I had started with, good question. If I had started with this, I omega t, right?
Mm-hmm.
Then I would ended up. Okay. That's very good question. Thank you.
Yep.
So when you ask me question, then I'll get to explain. Because sometimes I don't pay attention to something, right? So, yep. So let me rewrite this guy like this: V0 e to the I omega t. So then, after you do the calculation, you wanna do the calculation? Let's do it.
Sure.
Okay. So this is my, and this is my B, right? B is this. So then, what is your I? I equals C. This is C, right? Then what is the derivative of this guy?
I omega t v0 e to the I.
Omega e to the I omega t.
Mm-hmm.
Okay. Okay. So you know what? I can write this I can write this as e to the I pi over 2. My I is e to the I pi over 2. Really? Let's see. What is this? Let's expand this guy in terms of, what is this guy? Help me here. Cosine pi over 2 plus I sine pi over 2.
Mm-hmm.
So what do you get here? What is your cosine pi over 2? 0. Then what is your sine pi over 2? 1. 0 plus I times 1, which is I. See? My I can be written as this. Okay, so that's why I write this guy as this. C times omega e to the I omega t times e to the I pi over 2. Do you see that? So
Yeah.
then I'll combine these two guys. C omega e to the I omega t plus pi over 2. Look at that. Now,
Okay.
so how do you do this? Now if you expand this, then what do you get?
You would get
Cosine
line omega t plus pi over 2 plus
plus I
9 omega t plus pi over 2.
pi over 2. So when you did the, when you started, did you start with the imaginary or real? So
Imagine.
so in this case, this is called real, this is called imaginary, right? So in this case, we have, so what is the e to the I omega t? E to the I omega t equals cosine omega t plus I sine omega t. You started with imaginary, right?
Right.
That's what is yours. Then you don't have to take this guy because you started the imaginary. That's why you just take the imaginary part of this guy.
Okay.
That's why you have this guy here. Look at that.
Gotcha.
Makes
makes
sense? Makes sense?
Yeah, thank you.
All right. That's the beauty of complex notation. I like that. It is a very nice tool. All right, so that's what we are going to do now. So we are going to do the complex function, reactance as complex function, okay? That's the next goal now. Because we are so excited, so we are convert everything to complex function now, okay? So now now since I'm going to do the complex function, now I'm going to introduce a quantity called impedance. What is impedance? So resistance and reactance commonly called impedance. Okay. Okay. So man and woman we call human, right? In common is human. In the same way, resistance and reactance we call impedance. So impedance are of two types, resistance and reactance. Okay. Resistance. So resistance is R and reactance are RL and RC, right? Remember we did that before. Okay, for the help me, what is this guy? Inductance for the, this is for the capacitor, okay? So these are called, in commonly these are called impedance, okay? Now, since I know the Euler formula, right? Euler's formula, that's why instead of saying cosine omega t, I start with this now. Instead of B0 cosine, I have B0 E. So since I started with the real part here, when I do the calculation, I take the real part also, okay? Just remind me if I don't. Sometimes I may take real imaginary part also, if you have to remind me in that case. So then if you have V cos this, then what is your I? I is dq over dt, right? Then C dV by dt. So this is what we already know. Then C, what is your dV over dt? dV over dt is, I think we did that before, didn't we? But anyway, so V0 j omega e to the j omega t, right? If you take the derivative of this guy, C V0, C is already there. This is C, right? We are doing this dV over dt, C and dV over dt. So C and this is dV over dt. So dV over dt is V0 j omega, V0 j omega e to the. So this is what it is. Nicely, in nice way, I can write this guy as like this. Like this, right? Now, I convert this guy back to V again. See this guy? I'll convert this back to V. Then what do I get? J omega C V T. Okay. Now, let's find the impedance. Remember we call it RL before I introduce E to the thing, this thing, right? I call RL and RC, right? RL and RC, right? Okay. Now, since I introduced this thing here, okay, I'll rename this guy as ZL and ZC. Okay. So I change the name now. RL and RC becomes ZL and ZC because of this guy. So I have three impedances now. I have three impedances. One is ZR, one is ZL, the other is GC. This is simply R. ZR is nothing but R. And ZL is, let's figure out GL. So this is my This is my thing, right? So use the Ohm's law again. B equals IR, right? So B equals IR. So I equals, I have to write I equals rather, right? I equals, because you have I here. I equals B over R equals IR. So now let's compare these two guys. Compare this guy and that guy. This guy here. So what do you get? B is B. What is on the bottom? R. So BT over R, right? I have to write R. So 1 over J omega C. That's my GC. Does it make sense so far? So far, so good. Now I'm rewriting this guy. Normally what you do is, oh, by the way, remember I use J here instead of I. You know why? Because in electronics, we use I for the current, right? That's why to avoid confusion, we use J instead, okay? It's the same thing. So the thing is, remember we used to have the IA plus IB, right? Not like this, not A plus B over I. Not like this, we have like this, right? So that's why I is always on the top, not on the bottom, like this, okay? Not on the bottom. That's why our goal would be to write this J on the top. So meaning, how do I rewrite that? One is, what is J? J is square root of -1. What is J square? J square is 1, okay? So this 1 can be written as J square. J square on the top, then you have J omega C on the, oops, what did I do? Guys, I made a mistake here. This is -1. J square is -1 because I square this guy, then J square would be -1, not 1. Okay, this 1 can be written as G, 1 can be written as minus J square, little j. So this 1 can be written, this minus can goes here, right? So 1 can be written as minus J square here. Minus J square, this 1 is minus J square. Then on the bottom we have, what do you have on the bottom? J omega C. On the top minus J square, on the bottom we have J omega C. This and this cancel out. So you are left with minus negative J over omega C. That's your GC. This is called complex impedance of the capacitor. Does it make sense? That's how much time do we have?
I think we're actually out of time, Professor.
Oh, okay. All right, guys. Then I will stop it here. Any question?